In this video, we want to talk about a certain type of problem that is commonly asked in calculus textbooks and classes. It's a type of problem where you're asked to use the fundamental theorem of calculus, but not the evaluation theorem. Instead, you're asked to compute the derivative of various types of integral expressions that have your variable in the upper or lower limit. Consider this example that is written here. We're looking at the derivative with respect to x of an integral expression. That integral expression is an integral sine of a function of t with respect to t. The x appears in the upper limit of integration. There are different ways to solve this kind of problem, but I want to show you a way that will work for all of these types of problems. Anytime you're asked to differentiate an integral that has a variable in one or more of the limits of integration. So let's take a look at this. We're integrating sine of 1 over t. So this is a continuous function as long as we're staying away from t equals 0. If you have t equals 0, then you're undefined. But as long as you're away from t equals 0, this expression is continuous. And it looks like we're starting at 3 and going to some positive number, so it looks like our function is perfectly continuous as long as x isn't equal to 0. So x equals 0 must not be in the domain of this integral expression. All right. So how do we actually go about doing this? Well, the basic idea is to recognize that this integrand is our function little f of t. Normally we think of our functions as being functions of x, but there's nothing special about x. This can be a function of t. F of t equals sine of 1 over t. This, as we said, is a continuous function as long as we're staying away from 0. And it looks like we're doing that. So that means it has an antiderivative. We don't know what the antiderivative is, though. There's no way to write down some simple expression, some, as we call it, closed form expression for the antiderivative sine of 1 over t. But an antiderivative does exist. So we're going to just let it be capital F. Capital F prime of t is going to equal little f of t. So that is to say, capital F is an antiderivative of little f. We know that such a thing exists. We just don't know what it looks like. But what we do know is that capital F prime of t is equal to sine of 1 over t. Once you've made it to this spot, you're most of the way there. The thing that we're trying to do is differentiate this integral expression. But this integral expression is a definite integral. Don't be thrown by the fact that there's an x squared there. X squared is just some number. We're integrating sine of 1 over t with respect to t. So t is our variable of integration. If t is the variable of integration, that means x squared is constant. So this is simply a definite integral. And we can evaluate a definite integral using the evaluation theorem. So the integral from 3 to the number x squared of sine 1 over t dt using the evaluation theorem is the antiderivative of sine of 1 over t evaluated at the upper limit minus the antiderivative evaluated at the lower limit. So here we're using the evaluation theorem. This actually does pretty much everything we need it to, except for one thing. We just need to compute the derivative. You see, what we're looking at here is the derivative of a definite integral. The evaluation theorem tells us that this definite integral is equal to capital F at x squared minus capital F at 3. But what we really want is to compute the derivative, and that's great because we know everything we need to know about the derivative of capital F. Even though we don't know what capital F looks like, so we don't know what capital F at x squared looks like, all we care about is the derivative, and that we know. So the derivative with respect to x of the integral from 3 to x squared sine of 1 over t dt is equal to the derivative with respect to x of capital F at x squared minus capital F at 3. And again, we can't actually compute these quantities, but we don't need to. We just need to differentiate them. So this is the derivative with respect to x of the first term minus the derivative with respect to x of the second term. The second term is the derivative of a constant. F at 3, I don't know what it is, but it's constant. So that means if I differentiate it, I'm going to get 0. So instead, I just have to differentiate this term, which is capital F at x squared. This is a composition of functions. That thing is a composition. Composition of functions. Composition of functions. Because it's a function of another function, namely it's a function of the square function. So in order to differentiate it, we need to use the chain rule. So use chain rule. What does the chain rule tell us about this thing? Well, it tells us that, well, we're trying to compute the derivative with respect to x of this composition, f at x squared. So if we want to compute that derivative, we have to use the chain rule, and it's the derivative of the outside function. So it's f prime, the derivative of the outside function, times the derivative of the inside function. Well, the inside function is x squared. X squared. Well, the x squared still goes there. The thing that was inside is still inside. That hasn't changed at all. X squared, x squared. And then we're multiplying that by the derivative of x squared. And that's something that we can easily compute. Well, what is f prime of x squared? Well, we know what capital F prime is. Capital F prime of t is sine of 1 over t. Let me just rewrite that here. F prime of t is sine of 1 over t. So in this case, t is equal to x squared. T is equal to x squared. So f prime at x squared is equal to sine of 1 over x squared. So I just need to plug that back into here. And so we'll have sine of 1 over x squared times the derivative of x squared, which is 2x. And that's our answer. It's just that simple. The derivative of an integral, the derivative with respect to x of this complicated looking integral, using the evaluation theorem and the chain rule, is right here. It's sine of 1 over x squared times 2x. So that's our first example. Let's do another example. B. Let's compute the derivative with respect to x of the integral, and let's put x in both our lower limit and our upper limit in this one. So let's put the square root of x in the lower limit, and just for fun, we'll put sine of x in our upper limit. And let's put here e, let's say to the u squared du. Our variable of integration is u. I've been using t, but we're allowed to use any variable you want so long as it hasn't been used already. X is already used, so I can't put x's here, but I can put u, or t, or s, or r, any letter that you want as long as it hasn't been used. So I can't use an x, probably shouldn't use a d, probably shouldn't use an e, but I can use u. E to the u squared is another one of those functions, which is perfectly continuous, so it has an antiderivative. But if you try to write down what that antiderivative is in simple terms, you won't be able to. It has an antiderivative, but we can't write it down. But we know that it exists because e to the u squared is continuous. So let capital F of u be the antiderivative of e to the u squared. That is, capital F prime of u is equal to e to the u squared. Now again, I don't know what capital F looks like, but I don't need to know what it looks like. I only need to know about the derivative, because ultimately I'm computing the derivative here, d by dx. So let's proceed. The way we do it is the same. we look at the evaluation theorem. It doesn't matter that there's a square root of x in the denominator and a sine of x in the numerator. These are complicated expressions, but they're just numbers because x is given to us. We're integrating with respect to u. U is our variable of integration. So that means x is just some number. So the square root of x is a number, and sine of x is some number. So that means we can integrate from the square root of x to sine of x, e to the u squared du, by using the evaluation theorem. So it's going to be f at the upper limit, sine of x, minus f at the lower limit, which is the square root of x. So again, we're using the evaluation theorem here. Evaluation theorem. So, but this isn't what I need to compute. What I need to compute is the derivative of this definite integral. So we compute the derivative with respect to x of this definite integral, the square root of x, sine of x, e to the u squared du. This is going to be equal to the derivative with respect to x of f at sine of x minus f at the square root of x. So this is the derivative of a difference, so I can do each one individually. So this is going to be the derivative with respect to x of f at sine of x minus the derivative with respect to x of f at, let's call it x to the 1/2. Square root of x is x to the 1/2. It's the positive square root. Each one of these is a composition of functions. In both cases, the outside function is f. The outside function is f. The inside function is sine of x in the first one, and the square root of x, or if you prefer, x to the 1/2 in the second one. But I can use the chain rule on both of these. So let's look at the first one. It's f of something. So the derivative of f of something is going to be f prime of that same thing, but then I have to multiply by the derivative with respect to x of that inside function. That's the first one. Minus, and now it's the derivative of f of a thing. So the derivative of f of a thing is f prime at that thing, and then once again, I'm going to multiply by the derivative of whatever that inside function is, which is x to the 1/2. Now all of these things I can compute. The derivative of sine of x is cosine of x. And the derivative of x to the 1/2, we just use the power rule. That's 1/2 x to the minus 1/2. So what do we end up with? We have f prime of sine of x times cosine of x, that's a prime there, minus capital F prime of the square root of x times 1/2 square roots of x, just to write it in a slightly different way. But how do we compute these f primes? Well, what we know about f prime is that f prime of u is e to the u squared. F prime of u is e to the u squared. So here, in this first one, our u is sine of x. In the second one, our u is the square root of x. So for the first one, I just write u equals sine of x, in which case f prime of u is e to the u squared, so e to the sine of x quantity squared. And for the second one, u is the square root of x. So f prime of u is e to the u squared. Well, that's e to the x. Now putting all of this together, we have f prime of sine of x is e to the sine x quantity squared times cosine of x minus f prime of the square root of x is e to the x times 1/2 square roots of x. And that's our answer.